Okay. Hello, everyone. My name is Konrad Norowski. I'm from Instutite of Physics, Polish Academy of Sciences. More specifically, I'm from Kulfon group that was originated by Professor Maciek Zgirski. We mainly deal with the issues of thermal transfer at low temperatures. We deal with applied superconductivity. We like to build functional superconducting devices that allows us to infer about mechanisms of heat transfer, heat exchange, energy exchange with unprecedented temporal resolution. So this is our broad scope of topics. And today's topic is thermodynamics of a single vortex that we can manipulate. We like to call it a vortex on a leash because we can trap it in some specific device. We can expel it out of this device. We can measure the temperature dynamics because of this expulsion. But before that, I would like to tell you a little bit about how it went down to this point that we were able to publish this vortex dynamics paper in Science Advances. This is actually our biggest scientific achievement of our group to publish this article, and we have been dealing with the issue of this fast thermometer for quite some time, because our first articles treating these subjects, they were published in 2018, 2016 even. This is our main field of expertise. To go chronologically, we start with proposing fast thermometer based on a superconducting device that uses current pulses, and we were also able to study thermal correlation between these pulses. So this is important to obtain clean measurement in our systems, but this thermal correlations also can be a source of nice physics. For example, we were able to build artificial phase transition using temperature hysteresis that originated from these thermal correlations. So that was somewhat side quest or side project of our nanosecond thermometry, and the main part are in more general sense measurements of quasi-particle dynamics, so quasi-particle diffusion or quasi-particle recombination. That was our main scope for some time, but at some point we observed that our device that we use to measure thermal transient, that device is also sensitive to the presence of a superconducting vortices, and this observation resulted at some time in measurements of this vortex dynamics, where we somehow connected the utility of a thermometer and the vortex detector. So what do we need in order to measure this thermal dynamics of a vortex? We need a fast thermometer that is able to catch this dynamics. It must be fast enough to observe this fast processes of heat exchange mechanisms that can take place even in very low temperature. They are quite fast. We need a vortex trap, so a device that allows us to localize our vortex, so it's stable and it's not able to fly away on its own without our help. And we also need the method that induces this vortex dynamics, so some controllable way to induce this dynamics and to measure it actually. And when you bring all of this combined, you are able to obtain and understand our article from Science Advances that deals with these vortex dynamics issues. I'm going to divide my presentation on 3 parts. First part will be about this thermometer, second part about this vortex trap, and the third part is about vortex dynamics. And that also involves the method to induce this dynamics and to measure it. So first comes the thermometer. To give you a little bit of context about the general thermodynamics problems. So I show some very basic problem in thermodynamics. We have system that is thermally connected to the reservoir. So system can be, for example, electrons, and they can be connected to the reservoir of phonons by thermal link, for example, in the form of electron-phonon coupling, but they can be others. And this thermal link, it allows for the heat transfer between our system and its neighborhood and the reservoir. The simplest treatment of this heat transfer is to assume that this thermal link is proportional to the temperature difference between our system and the reservoir. So if the temperature difference is bigger, the heat transfer is also bigger. And this observation leads us to the differential equation that governs the dynamics of the temperature of this system. So I enclose this differential equation here. And it has a very simple solution in the form of an exponential decay with the decay constant or a relaxation constant consisting both heat capacity, that is a property of the system, and thermal conductivity, which is a property of the thermal link between the system and its surroundings. And now the issue with the fast thermometry is the fact that the thermal processes that we study, they are relatively fast. So the slowest of them, they have characteristic times of the order of 10 microseconds, but the fastest they can extend to several tenths of nanoseconds. This is rather fast. These processes can be rather fast, and in order to catch them, we need a fast and reliable method to trace this temporal dynamics. And how is this important? Why is this actually important? This temporal resolution I'm showing here. So here I graphed I draw the graph for the thermal relaxation with the relaxation with the decay time of 100 nanosecond. And let's focus on the left for the beginning. Let's focus on the left graph. If the bandwidth of our measurement method, the method of our dynamic thermometer, if its bandwidth is considerably bigger than the relaxation, this is generally not a good idea, because during the measurement window, the system can relax to the equilibrium. So the temperature varies a lot during the measurement. This is not a good idea, because because that then it's hard to determine how to think about it, because in the one measurement event the temperature varies a lot. It's not stable. On the contrary, if your bandwidth is much lower than the characteristic time of the process you are able you want to measure, the situation is completely different, because for the short bandwidth the temperature is varies to a much smaller extent, so we are able to probe this temperature dynamics much more precise. So this is the reason why we need fast thermometers. We need to keep up with the pace of fast changing thermal processes in the nanoscale. What are the thermal processes we want to measure? On the left, we see the very simplified structure of our sample. So we use aluminum structures that are evaporated on a silicon. The silicon is just a substrate, and the substrate is glued to the sample holder, which results in a combination of thermal subsystems described on the right side of this slide. So we have a system of electrons in the aluminum. They are coupled through this electron-phonon coupling channel to the phonons of this metal. And these phonons are further coupled to the phonons of the substrate, and the substrate is coupled to the holder. So this is these are electron-phonon couplings and phonon-phonon couplings. But apart from that, electrons can change their energy, but by absorption of some irradiation, some photons. They can radiate this energy also, and they can also diffuse through our device, and they can also acquire energy from Joule heating, obviously. So these are the thermal processes we aim at measuring them. What are the timescales? Because I said a lot of the necessity of having this fast thermometers. So here I drew thermal processes and their characteristic times, and thermometers with their temporal resolutions. So on the right side of the axis, we see thermal processes. We have electron-phonon coupling that can range to this tens of nanoseconds. We can have electron diffusion, which is length dependent, because this is diffusion. And in metallic microstructures, this characteristic diffusion time can be even lower than a single nanosecond. We have phonon ballistic propagation. So depending on the characteristics of the movement of phonons inside system, they can move ballistically or diffusively, but ballistic propagation is thought to be faster, so it can extend from hundreds of nanoseconds to much smaller than nanosecond. And we have also time scale for interaction between electrons. So this is time scale at which electrons agree their energy between each other in order to have proper Fermi-Dirac distribution. So these are thermal processes, at least part of them, that we aim to measure. And now regarding thermometers, the red bar indicates the temporal resolution of the old methods of dynamic thermometry, I mean older than the methods that were previously available in the field before our invention of switching thermometry. So this comprises mainly reflectometry and transmission of radio frequency signals. And now we extend this temporal resolution by introducing our method. And in fact, now we are somehow and now in fact this is even not a final word for this method, because fundamental limit of the temporal resolution of our method is in fact even farther in faster time scales than we have now. And with the proper equipment, we hope that at some point we would be able to measure even faster processes. So maybe very fast diffusion or very fast ballistic propagation of phonons, for example, or maybe even faster processes that we are not aware of now. Superconducting thermometer, our sample. Our sample is in the form of a diam nanobridge, which is a constriction embedded inside a superconducting nanowire. Such nanowire, its advantages are as follows. They are very easily prepared. One can prepare such structure quite fast, in one day probably, or something like that, because it requires only the usage of single-step lithography with evaporation, e-beam evaporation, or Joule heating evaporation. And what is important is the fact that this structure, it has temperature-dependent transport properties, which makes it ideal for the utility of the thermometer. And apart from that, it has fast intrinsic dynamics. So the structure can decide very quickly to switch its state in a response to the changing temperature. So this is the reason why it can serve as a fast thermometer. On the right side, we see IV curve, current voltage characteristics of such a sample, such a wire with a constriction embedded inside it. In the middle of the panel, we see zero voltage drop vertical line, which indicates zero resistance. And upon exceeding some current, we see that we are able to transit from zero resistance state to the state of a finite resistance, which can be attributed to the normal state. And now we call this transition from the superconducting to the normal state switching. And the current that switches this junction, we call it the switching current. What is the origin of this switching? One can ask. So to explain it, I would like to discuss what happens when we bias such a structure near the transition. So near this switching current. So if we treat our system quite naively as a system completely without fluctuations, we expect that our switching current will be time independent. We would have very stable value of switching current, and in such a case, when we send current pulse with an amplitude lower than switching current, there would be no switching. And if our current exceeds switching threshold, switching will inevitably happen. But our world has fluctuations always, be it the thermal fluctuations or the quantum fluctuations. So this switching current fluctuates with time. This is a way to imagine it. So now, even if we send two identical pulses, one can result in no switching because threshold for switching is above the current level. And another time, switching can happen simply because the fluctuations allowed it to happen. So we thought about the switching as a stochastic transition process. So this is a transition process that is governed by inevitable and random fluctuations. So the transition has a stochastic character because of it. Another way of showing this effect of fluctuations is here. On this graph, maybe I exaggerated a little bit the range of the fluctuation of a switching current, but this is just only to show you qualitatively what is going on in the system. So as we can see, there is a possibility for sending relatively high current and observe no switching, again, because switching threshold can be above the value of the current that we send. And on the other hand, we can send rather low current pulse, but fluctuations can help us in the way that fluctuation can lower the switching current threshold. And in effect, high current can lead to no switching, and low current can lead to switching. So we see that this switching is a stochastic property. So we strive to describe it using switching probability. So probability for switching to happen for a given current, for example. So on the left part of the slide, we see how the switching situation would look like without the fluctuations at all. So we have some switching current, and upon exceeding it, the probability is 1. Below this threshold, the probability is 0. But when fluctuations come to a place, this transition is smeared. So there is a possibility that low current can induce switching, and sometimes high current can result in the lack of switching because of these fluctuations. So how we measure this probability actually? We send many pulses on this superconducting weak link. We send current pulses, and we measure response of the system in a form of a voltage drop pulses. So if the pulse if pulse switched the junction, we observe voltage drop. If there is no switching, despite the fact that we send current pulse, there is no voltage drop. So to estimate the probability that comes from such a measurement, we divide number of switchings that we can count by the number of all pulses that were sent on our weak link. So this is estimation of a switching probability. The number of switchings per number of pulses. Now, what is important is the fact that the switching probability is current dependent. And we can measure it, for example, in such a way. So at first, we send current pulses that have high amplitude of a current. So it can result in switchings in all cases. So probability is 1. We can also send low current pulses, low enough that the fluctuation cannot help them to switch the junction. So this is the case where we have no voltage drops, so the probability of switching is equal to 0. And in between, in quite narrow range of approximately 1 microamp, we have a region where this stochasticity comes to a place. So sometimes we see switching, sometimes we see no switching. So we have non-zero and non-one probability. And now such a curve that describes probability versus testing current is called an S-curve because of its shape, or because we can call it switching curve. Now the position of this curve is temperature dependent. And this means that in lower temperatures, it's harder to switch the junction, so you need higher currents. And in high temperatures, it's easier to switch this junction, and you need lower current. So you measuring this S curves in various temperatures, we are able to obtain the relation between center of this S curve. So center of this S curve is described by the current that results in a switching probability equals 0.5. So we are able to measure the relation between switching current and temperature. So this gray line shows us the intersection between probability 0.5 and the current values that describes center of these S curves. So now this switching current versus temperature can act as a calibration. So now we have switching current versus temperature. So if one measures some thermal processes, and at some moment of thermal process we measured switching current to be of some value, we can convert this switching current to the temperature. This is one of the ways to calibrate our thermometer using switching current. But apart from switching current, we have also switching probability, which is also temperature dependent, since this S curves they can shift due to the change in temperature. So here the situation is a little bit different, because we are dealing with probing with constant testing pulse amplitude, for example, this 56 microamps. So we see that these S curves that varied with temperature, the temperature for the given testing pulse amplitude influences the probability. So we can use probability versus temperature in order to obtain another calibration for our measurement. So this is probability versus temperature that one can obtain. And we are especially interested in the linear regime, because here the calibration is especially simple, because one just need to fit a slope, and that's all you need to have in order to obtain a calibration factor between probability and temperature. And so now we have a way to convert change in the probability to the change of the temperature during the thermal transient. And now, sorry for a moment. So now we have two calibration method to measure this thermal transient, and we need to have a way to induce this transient. For now, without vortices. I will come to the vortices at the third part of this presentation. So now the pulse pattern is a little bit more complicated, because apart from the testing part that checks the probability, we also stand on our junction, our weak link, diam nanobridge. We send heating pulse, and its purpose is to switch the junction and overheats the junction So it has the temperature over Tc, but with time, the structure cools down, and we can trace this cooling. In this case, temperature changes, so probability changes too, and then we vary delay between heating and testing. So we can check the probability for different separation times between heating and testing. So for every delay, we measure probability for every delay point that we chose to measure. Since we measure probability, for every delay, we must send pump and probe many times, for example, 1,000 times. So say we chose delay equals 2 microseconds, we send heat test, heat test, heat test, and 1,000 times in order to obtain probability for this given delay. And using such pump and probe repeated in order to measure probability, we are able to measure, for example, relaxation after this switching. We are able to recreate cooling curve in such a situation. And then we are able to fit the exponential, because as we see, the cooling agrees with this simple exponential cooling law. And in this case, relaxation time is of the order of hundreds nanosecond, which is close to the edge of the temporal resolution that other methods are able to provide. But in higher temperatures, it is very easy to obtain relaxation times of the order of tens of nanoseconds, and these processes are not they are simply too fast for these old methods to catch. So to summarize the first part of my presentation, our DIAM nanobridge is fast and sensitive thermometer. It allows to measure this fast thermal processes. We use switching current or switching probability as a temperature dependent properties of our weak link. And during the induced thermal transient, the switching current and switching probability change with time. So using calibration, one can calculate their dynamics to the temperature dynamics. And once again, to reiterate, we measure switching, which is a stochastic property. So we need to perform our pulse pattern many times. So that would be all about the thermometer. Now it's time to vortex trap. So we have some structure that allows for the trapping of a single vortex. For example, here we see a double vortex structure, and it's possible that, for example, in one trap there is a vortex, and in another one there is not. To give you again, to give you some context and to remind you the basic properties of a superconducting media interacting with the magnetic field. When we have some material that is normal, non-superconducting, magnetic field flux lines can thread the material without any disturbances. In superconducting materials, in the first kind material, we have something called Meissner state. We have screening currents that expel the magnetic flux field lines from the sample. But in second kind superconducting materials, we are able to observe vortex phase. So vortices are circulating currents that encircles the areas where the magnetic field lines thread frets our material, and these are the areas where the superconductivity is suppressed. What is interesting is the fact that the nanostructuralization of the material can bring the first kind superconductor to the second kind superconductor. So, for example, aluminium has this property that in bulk, it is a first kind material with very well developed Meissner state, and in second kind, when we and it can be nanostructuralized in order to obtain second kind superconductivity with the vortices present in superconductor. This is the vortex trap. As you can see, the structure is very easy. This is just a nanosquare with the width of the order of 1 micrometer or close to that. And now there is a formula that governs the first vortex entry with the field of first vortex entry with the width of this trap. I will talk about the reasons for this formula in a moment, but for now let's check what is the order of magnitude of this first vortex entry. So, for example, here we have a 1 micrometer width vortex trap. So yeah, one micrometer, and flux phi0 flux quantum is of the order of 10 to the minus 12, if I remember correctly. So and p over 4 is 1. So so the first vortex entry for such a structure, for such a vortex trap, would be around 2 millitesla, based on this formula. And what is the origin of this formula? It is the fact that this entry field B0 results in a magnetic flux threading this square equals to flux quantum. That's just it. From the more thermodynamical point of view, we can think of it in such a way. On the left side on the slide, I drew the free energy for the vortex trapping. And these are cross sections along this orange line on the SEM of this vortex trap. So for low magnetic fields, there is no minimum for the vortex trap to be present inside. At some point, the free energy develops a flat band inside this vortex trap, and this is the first moment that allows for the vortex entry, because if you raise the field a little bit more, you would end up with an energy minimum, and energy minimum is all that one needs in order to have this vortex trapped inside our structure. And then by raising magnetic field higher and higher, the entrapment of this vortex becomes stronger and stronger. How to trap this vortex in our structure? So we perform field cooling procedure. So we apply magnetic field that is close to this first vortex entry field. And once again, we need to have heating, but now just in order to introduce critical temperature in our system for a moment, because when your structure is overheated. It's in normal state. It cools down. At some point, it will surely have critical temperature. In critical temperature, there are no barriers for this vortex to enter from the continuum to the inner part of the box. So this thermal reset pulse serves only as a source of heating for the vortex entry. Then we wait quite a long time in order for testing not to see heating from this reset pulse. So it sees some equilibrium temperature and it is able then to see if the vortex is present or not. So once again, reset pulse switches the junction and box, bringing their temperature over critical temperature. And over TC field lines can enter the box. At TC, vortices can be trapped inside this box, and below TC there is a stable vortex phase. So this is field cooling procedure because all of this is taking place at some constant magnetic field. Now we check the transport properties of such a structure. So we have vortex trap with a dime nanobridge connected to this vortex trap. So now we measure switching current in a function of a magnetic field. The first part, the part that is closest to the zero magnetic field, is rather easy to interpret because this is a reduction of a superconducting order parameter because of the rising magnetic field. So one can think of screening currents or something like that. After this, we observe a drop, sharp drop of a switching current, and this drop is an indication that the vortex entered our system. I will talk about the origin of this drop in a moment, but now I would like to show you some more extravagant transport curves for your curiosity. So, for example, here we see double vortex box, and the presence of another box clearly influenced the shape of this vortex, the shape of this current characteristics. Here, for example, we are able to observe some steps in these dips that comes from the fact that sometimes one vortex is present in the box, sometimes two vortices are present in the box, and all of this can be proven by Ginzburg-Landau simulations. So we've had a cooperation with a simulation group from University of Antwerp, and they performed for us time-dependent Ginzburg-Landau simulations. And we see this the outcome of this the simulations on the right side of the slide. So this dark circles are vortices. So this is a suppression of the superconducting order parameter, and this lighter areas are just unharmed superconducting areas. So we see that one is able to obtain a situation where we have vortices in both boxes. Sometimes one box can have multiple of vortices, and it can even have different number of vortex than the other box. Coming back to the issue of first vortex field, we said that this first vortex field is inversely proportional to the square width, and we measured that it is so. So on this figure, you can see on the y-axis this first vortex field entry. So the measurement of the field that resulted in a first vortex entry, and on the x-axis we see inverse with squared, and we see that all our structures that were measured that consisted the boxes, they lie on one slope. So there is one proportionality coefficient. What is interesting, nanowires lie on nanowires without vortex boxes. They lie on another slope, and the expected curve from this pi over 4 phi 0 w over w squared law is this blue one. So it differs a little bit from the experiment, but in fact this curve is very reliable, and we were able even to engineer field that results in a first vortex entry by choosing the proper width. So we chose width, and we end up with the field of our liking. To sum up a little bit, our dime nanobridge can have a property of a vortex sensor and the thermometer. So it can sense the changes in the temperature, and apart from that, it can see the vortices because of this sharp drops in switching current versus magnetic field. So this is summary of the second part. In a moment, I will talk about, finally, I will talk about this vortex dynamics. But to summarize, we see that we developed this superconducting box, and vortex trapping is surely possible within them, and that was confirmed from experiment and Ginzburg-Landau simulations. This magnetic field of first vortex entry is geometry dependent because it relies on the width of this vortex trap. We can engineer this first vortex entry field, and switching current of our bridge is sensitive to the presence of these vortices, so they can act. These nanobridges can act as detectors for the single vortices. Now the long-awaited, I hope, part is about vortex thermodynamics. So now we will use our electrical pulse paradigm in order to try to expel the vortex using this current pulses from the trap, and measure what happens after this expulsion or trial of this expulsion. So now the pulse pattern will be a little bit more complicated. Again, we need to add another pulse, but I will explain everything in its own time. Coming back to this, I said that the presence of a vortex lowers switching current. This is this sharp drop in a switching current, and the reason why is it so is the fact that current can expel vortex. So this testing current that we send on our junction, it has the ability to expel the vortex, obviously when the vortex is present in our box. So this expulsion results in an energy dissipation, and energy dissipation equals elevation of the temperature, and elevation of the temperature changes the switching current. So if the temperature is higher, then switching current is lower. So this drop is actually a fingerprint of a vortex being expelled from the box, from the vortex trap. And now I will focus more of this vortex entry, vortex expulsion area. And it is interesting to think how to get rid of this vortex. So now, in order to get rid of this vortex that is causing a dissipation sometimes, we add another pulse to our pulse pattern. And this is called Lorentz pulse. It is called Lorentz because it exerts a Lorentz force on this vortex, so it can expel the vortex before testing does it. So let's check what the addition of this Lorentz pulse can do to this area of the first vortex entry. So Lorentz pulse equals 0 microamp is exactly the same curve that I presented in the previous slide. But if you send Lorentz pulse high enough, you are able to elongate this non-vortex state. So this is such a situation that Lorentz expels the vortex. Then we wait some time so the system equilibrates. And then by the time testing arrives on a junction, there is no vortex to be expelled. So we can still study non-vortex state, despite the fact that the vortex was in the structure a moment ago, but we expelled them using Lorentz pulse. So this is a way to elongate this non-vortex state. Now, what we want to see is how switching current will change when we vary the value of this Lorentz. What happens if this Lorentz pulse is small? What happens if this Lorentz pulse is high? And this is what is happening. On y-axis you see switching current. On x-axis you see value of Lorentz pulse. So if your Lorentz pulse is 0 or if it's small, this Lorentz pulse cannot expel the vortex. So by the time testing pulse arrives, the vortex is still present in the vortex box. And because of it, testing expels the vortex and it results in a dissipation. Because of this, junction feels high temperature and it results in a low value of switching current. So this low value. On the other hand, if the Lorentz pulse is high enough, so say from 70 microamp or something like that here, the vortex is expelled on a Lorentz pulse during the Lorentz pulse. Then we wait for the system to equilibrate temperature, and we see that that testing sees high switching current, so low temperature. Okay, now we want to see what will happen if we measure the same thing, so switching current versus Lorentz pulse value, but now we vary magnetic field. So on x-axis, you have again Lorentz pulse. On y-axis, now you have magnetic field. And switching current is in colors. So, so from blue, you have low switching current, to red, high switching current. Because of what I said earlier, now let's focus now on this area of 2 indicates by Roman numeral 2. You are able to have absence of vortex during testing. So these red triangles, and it corresponds to this high plateaus of switching current. So high switching current. And you have also blue areas where Lorentz pulse was not strong enough to expel the vortex. So once again, we have a situation where we have testing induced vortex expulsion. So testing pulse expelled the vortex, and there was an elevation of a temperature, and in an effect, you have flow switching current. Now on this vortex stability diagram, on this vortex stability map, we have a multiple of different edges and areas. So for example, what is important is this are these tilted slopes of an expulsion current. So this is the edge that do you see my cursor? Because I'm not a yes, Professor Witlin?
Yes, we do, yes.
Oh, okay, thank you. That would help a lot. Okay, so these edges, this one and that one, they indicate the value of the level that that results in a vortex expulsion. So here there is no vortex expulsion on level, but here there is a vortex expulsion on level. So we see, so we can see using this map a relation between expulsion, be it the positive or negative value of the Lorentz, expulsion current in a function of magnetic field, and we see that it rises. So the stronger magnetic field you have, the stronger current you need to apply, the stronger Lorentz pulse you need to apply in order to expel this vortex. And this is common sense. This is very good. Yeah, and again, we see high switching current area, this red area, and low switching current area also here. So horizontal cuts of this map are equal to that. So this measurement was for some chosen value of magnetic field. So this map consists of such curves measured for different magnetic fields. So y-axis. As I said, we have a multiple areas of this vortex map. So this vortex can influence the switching current in many ways. We see vortex stability map. We see switching on right, this right panel is switching current versus magnetic field. But here I enclosed also descriptions of these areas on the bottom side, sorry, on the bottom side of the slide. And now what you need to remember is the switching happens when you have this red lightning symbols. Starting from the most simple first area, this is Meissner state area. You have no vortex, so you can only switch. At some point of a current, you switch. So you go from zero current to some value and you switch. Then you have in the second area, you have the situation where you can expel the vortex, as I said, and this is this situation because you expel the vortex and it results in a lowering of the switching current from this to this. So you go. So the testing goes from here. It expels the vortex, and it goes here where it switches the junction. So this is sorry. So this is the blue. This is the blue area. Now the red area goes like this. Lorentz pulse expelled the vortex. So there is no vortex to be expelled, and you go here because this expulsion threshold was done. Exceeding of this expulsion threshold was done by the Lorentz, and now testing pulse goes here, and you see high value of this switching current. What is also interesting is the third area, because here level cannot do anything. We see it because the color is uniform along x-axis, so level does not influence the switching current. So now testing goes up and up until this point. We expel the vortex, and the switching current lowers from this to this, but we apply current of the value here. So we are above the switching current. So we immediately switch the junction. So this is this area here that is a natural continuation of this slope here. So on this line, switching current is equal to expulsion because of what I said. And the last area is the fourth one. Here the situation is again relatively simple because we have stable vortex. So the expulsion current is higher than switching current. So the junction will switch first before we obtain the current value high enough for the vortex to enter, to leave the vortex trap. So we switch before we switch without the vortex expulsion. The problem with this map is the fact that it was measured for the constant delay between Lorentz pulse and testing pulse. So this delay was chosen in such a way that we do not see thermal effects originated from Lorentz that can influence the switching current. And now let's vary this delay in order to observe this temperature dynamics. We can qualitatively see three traces that originate from this map. So the simplest case is that the field is too low, so there is no vortex and no dynamics, the blue curve. Then again, we can have the situation where Lorentz pulse is weak. So vortex is in box during testing, and instead of Lorentz, testing expels vortex. So rise of the temperature is here. So the delay cannot influence it. So regardless of the delay value, we see some high temperature. Although this measurement can be useful because it shows what is the temperature during the testing, but okay, it cannot show you the dynamics. And what is the most interesting part is the value of magnetic field and Lorentz pulse here. In this case, Lorentz pulse expels vortex, and testing traces temperature change because heat production was here, and then we delay this testing with respect to the moment of the heat production. So we are able to measure change of the temperature with time. So this measurement was originally in the form of a switching current versus delay, but we converted switching current to the temperature. And we see that the relaxation time is rather rather close to the value that was obtained without magnetic field, although it's a little bit faster because of the lowering of the superconducting order parameter because of this magnetic field. And we see that our thermal effect is of the order of 200 milli-K, a little bit more than that. We can then calculate the energy released in such expulsion event. In order to do it, we just need to integrate superconducting heat capacity from bath temperature to the temperature immediately after vortex expulsion. So we just need to integrate the superconducting heat capacity, which has the shape of as follows. So this is literature value of superconducting heat capacity. So we have 400 milli-K bath temperature and 625 milli-K because of this value, and we integrate from here more or less to here, and this energy is equal to 4.3 times 10 to the minus 19th joule, which is approximately 1 electron volt, which is again energy of a single photon of a visible light. So this is quite a big amount of an energy, I would say. We can also measure energy released in a function of temperature. So we measured from 0.3 Kelvin to 0.8 Kelvin. But the order of magnitude does not change. This energy lowers down a little bit. And this is basically all. So to summarize, we trapped and expelled superconducting vortices on demand. We measured temperature dynamics due to this expulsion. This temperature dynamics, it was mainly governed by phonon emission, but the influence of this electron diffusion term that I discussed briefly at the beginning can be also discussed. Expulsion energy in the order of 10 to the minus 19 joule. This expulsion current, what is important, scales with magnetic field. And we also observed something called vortex diode effect, which is the fact that expulsion currents for positive and negative current, they differed a bit. And this, so we answered some questions, but these results raised another question. So what is the origin of this vortex overheating? Is this dissipation due to the vortex movement inside the box, or maybe the dissipation is only during expulsion? So in the field, there is an uncertainty about it. Theoreticians discuss about it a lot. So at some point we aim to resolve experimentally this issue. And again, one last thing, what is the dynamics of the vortex expulsion? Because we measured thermal trace of this expulsion after. We measured thermal trace after this expulsion, but we were not able to measure during the expulsion. So the theoretical expectations for this dynamics is in the picosecond range. So we are still too slow to measure it. At the end, I would like to advertise our site, Coolphone Group site. We put all of our seminars there, posters and article. So you can visit anytime and see what are our newest achievements. Here I enclose the bibliography, and this is the last slide. I would like to thank you for the attention, and I am open for questions. I see I took a little bit more time than I anticipated, so sorry for that, Professor.